All right, so today we are going to talk about how integrals relate to volume. And so one of the things that we talk about is that basically an integral is a sum of a whole bunch of stuff. And if you take an area of a region and you spin it around an axis, what you're going to end up with is a solid or something that's three-dimensional. And that three-dimensional shape is illustrated down here. If I take this region right here and spin it around the x-axis, I will end up with this vase-shaped figure over here. Well, when you spin that around the x-axis, if I look at the vase-shaped figure that's remaining, what you're really going to see is you're going to see that each of these individual cross sections, if I were to slice it perpendicular to the x-axis, are a whole bunch of tiny little cylinders. So if I were to segment this, I'd have a whole bunch of tiny little cylinders that together make up the entire vase. Well, if I wanted to add together all of those tiny little cylinders, the volume of a cylinder, this would be my radius, that would be my height, the volume of a cylinder would be pi r squared h. Well, if I'm dealing with these cylinders and they are taken perpendicular to the x-axis, my height is some infinitesimally small distance that's a change in x. In calculus, we call that change in x dx. So our volume really becomes pi r squared dx. And then if I'm adding a whole bunch of volumes together, that's where the integral comes in. So if I quickly erase all this, we'll come back to it in a moment. And oops, wrong thing, and I swing back up here, the volume of a solid with known integrable cross-section area A of x. That sounds really complicated. All it's saying is when you have a volume and you take a cross-section and you get that cylinder, this would be the area. Wow, that disappeared really fast. This would be the area in question right here. This is the cross-sectional area, is that circle right there. So if I have a volume of a solid of known integrable cross-section area A of x from x equals a to b, the volume is the sum, or the integral, from a to b of a of x dx. Now you might be thinking, wait a minute, this is volume. How come all of a sudden I have an integral with area? Well, you don't really have an integral with area. If I have something that has a circular cross-section like that, but also has a depth, the volume of a cylinder is pi r squared h, where pi r squared is the area of the circle, and h is like your depth. Here's the area, here's the depth. And area times depth is going to give you volume. All right, so now if we want to talk about the volume of a disk, like we've been discussing up there, this integral that we were just talking about becomes this integral where a of x becomes pi r squared and dx stays dx. Now, if we're going to revolve a region about an axis and the region completely touches the axis, our cross sections look like discs. I always say to picture a hard-boiled egg, because if you think of a hard-boiled egg, you've got that inside yolk part and then the outside. If I have it solid, I have that hard-boiled egg with the yolk, it's a solid disc. All of our cross sections have a face of a circle, so the area of each face is pi r squared. All right, so now let's actually do it here. The region shown here is 2 plus x cosine x, negative 2 to 2. Find the volume of the solid created if the region shown is rotated about the x-axis. All right, what I always do with these is I draw what's called a cross-sectional area. So I draw in one of my representative rectangles here, and I say, all right, if that's going to spin around the x-axis, it's going to look something like this. I'm going to have a disk. The width of that disk is dx no matter what. The height of that disk is my radius, and my radius goes from the x-axis to the curve. So my radius has a value that's just the equation of the curve. The volume of the resulting solid from the, we'll call it the formula above, is the integral from a to b of pi r of x squared dx. Well, what do I mean by r of x? That means the radius in terms of x. Well, I have that. It's right here. So the integral that I'd be looking for would be the integral from -2 to 2 of pi 2 plus x cosine x squared dx. My integral would be pi r squared h. And then from there, it doesn't say anything about calculator, so we would use our calculator for this one. So take a second and take out your calculator and evaluate that integral, and you should get an answer. Take a second and do that. Hit pause if you want. And if I had a calculator, I could do the same. Unfortunately, I don't have a calculator on here, so just get your answer and plug it right in. If you give me a moment, I could actually pull an answer up. Hold, please. Okay, I'm back. I found a calculator. So if you type that into your calculator, making sure that you are in radians, which is always what you need to be in when it comes to calculus, you should end up with an answer of 52.429. And that is the volume of the vase. So let's just move ahead and do another one, because honestly, these are not very difficult. Once you get the hang of it, it should be a piece of cake. Find the area in the first quadrant bound by those curves and below by the x-axis. Find the volume when you revolve it. So first they want me to find area, but I can't do that until I see a picture. So if I have the square root of x and y equals 2 minus x, and I want the area in the first quadrant bound above by the radical and that, and below by the x-axis. So it tells me that both of those are above and the x-axis is below. The only thing that is enclosing that, which includes the x-axis, would be this shaded region right here. So if I want that area, I need two integrals. And for the volume, I'm actually also going to use two integrals. So my area here is going to be the integral from, well, I need to figure out where they intersect. So where does 2 minus x equal radical x? Well, we can do that on the calculator. So I would like you to hit pause, find out where those intersect, and then come back to see if you get the same thing I do. So if I want to figure out where 2 minus x equals radical x, we should end up with, just making sure I get the same thing you do, x equals 1. So at x equals 1, I'm going to have the integral from 0 to 1 of root x dx. That's going to be the area of this one piece. Here, I'll take away my 1 and take away the shading for a second. Technically, this is broken up into like a red region and a green region. We'll call it purple. Sorry, I grabbed purple instead of green. So if we do red and purple, this is going to be my red region for this piece right here. Here, I'll even color it red for you. Look at that. Now it's red. It should be red. Come on, you can do it. There we go. So I'm going to have the red region, and then I am also going to have the purple region from 1 to 2, because this would cross the x-axis at 2, where I have 2 minus x dx. That's going to give me my area. So if you quickly put that into your calculator, 0 to 1 of radical x plus the integral from 1 to 2. If you type this all into your calculator, I'm getting a value of 1.16 repeating. I know I always tell you 3 decimal places. 1.16 repeating is technically more than 3 decimal places, so if that ever occurs, feel free to put the bar over it. You're still covered as for the 3 decimal rule. And then if we want to find the volume when I revolve around the x-axis for the red region, my volume is still going to have the same bound, 0 to 1, because my red region is enclosed right here. Well, the radius of that red region would just be the equation the square root of x. So from 0 to 1, I'm going to have pi r squared dx. And then for my purple region, still the region from 1 to 2, I'm going to have pi r squared dx. And then we just want to plug that into the calculator and see if you get the same thing. The nice thing is if you hit the second enter button in your calculator, this ends up working out quite nicely because you can just plug in a lot of that stuff and just square it, which is exactly what I'm doing off screen right now. And in a moment, I should have an answer for you. And I'm coming up with an answer of 2.61799, so I'm going to say 2.618. There is your answer, and we should be good. All right. All right, and on to example 3 here. Let me make the page a little bit bigger. Don't need this. Sorry about this, technical difficulties here. So if we want to find the volume of the solid created when the region in the first quadrant, blah, blah, blah. All right, so let's sketch it. Enclosed by the y-axis, y equals 5, and y equals x squared, is revolved around the y-axis. All right, so the first quadrant region means that I'm just going to consider this part. And I'm revolving this around the y-axis now. All right, so if I spin it around the y-axis, all of my disks now, I'm going to have to slice this way. So my representative disk looks like this. It's horizontally oriented, which means my height now is dy, and my radius now needs to be a radius in terms of y, like r of y. So if I want to get my radius in terms of y, because I'm using dy, I've got to come back up to the equation of the line, make it x equals the square root of y, and that goes there. So the volume of the resulting solid is going to be pi r squared h from 0 to 5, because those are my y bounds. And this one I can do by hand. So this is going to be 0 to 5 of pi times y dy, which is going to be pi over 2y squared, from 0 to 5, which is going to be 25 pi over 2, technically minus 0. All right. And example 4, find the volume of the solid created when the region enclosed by that and the y-axis is revolved around the y-axis. Well, it's in terms of that, and how are we going to graph this in a calculator? Well, you know what? You're just going to pretend that all of these y's are x's. So all you're going to do is say, you know what? We're going to graph y equals x squared plus x minus 2, and we're going to look at the x-axis instead. And we're going to revolve it around the x-axis instead. I'm just changing all the letters around. Everything will stay the same. So for this next one, if I have x squared plus x minus 2, let's see, that's going to have roots of negative 2 and 1. So I'm going to graph it like this. And I want to know where it's enclosed by the x-axis. So I'm going to enclose it right there. And I'm going to spin that around the x-axis. Again, I know it says y-axis, but we just changed everything, so we're okay. This goes from negative 1 to 2. Again, I know that because I just kind of factored it in my head. Oh, I just said it wrong. I didn't mean negative 1 to 2. I meant negative 2 to 1. Pardon me. Because when I factor this, I get plus 2 and minus 1. So my boundaries are going to go from negative 2 to 1. And the thing I'm spinning is this little red rectangle here around the x-axis. And the height would just be the function's value. So my radius is just going to be x squared plus x minus 2. So pi r squared dx. And from there, you're just going to plug it right into your calculator, which I am doing off screen right now, from -2 to 1. Make sure you watch your parentheses as you do this. They are incredibly important. Make sure you're squaring the whole thing. Make sure you have your pi in there. You can always pull the pi out in front if you want to as well to make the integration part easier. And I'm getting an answer of 25.447 if I round. So that is integration with respect to disks when there are no holes in anything. The next part of the notes that you will see is going to be holes.